So in a conducting wire, the net charge is zero, so they don't produce electric field, but the moving charges produce a magnetic field. Okay. Okay. So here's what this problem is about. So you see, this equation tells you moving charges currents produce magnetic fields. Okay. This term looks exactly like that term. So changing time varying electric fields act like a current. Okay, and this is called the displacement current. Okay, so the displacement current density is given by epsilon naught del E by del T. That acts like a current, and that'll produce a magnetic field. Okay, and you guys know that a straight long wire, if you have a straight long wire like that, it produces magnetic fields like this. You stick your thumb out in the direction of the current, and the magnetic fields are like that. Okay. All right, so similarly, if the electric field is increasing in this direction, it acts like a current in that direction. Okay, so that's what this problem is about. Okay, so express the displacement current in a capacitor in terms of the capacitance and the rate of change of the voltage across the capacitor. So what you want to keep in mind is here's a parallel plate capacitor, and as current is flowing into the capacitor, as current is flowing in, the charge is increasing on the capacitor, and the electric field is increasing. The strength of the electric field is increasing. Yeah. So the displacement current is given by epsilon naught del E by del T. Okay, and the electric field in the capacitor is voltage divided by D. So we're going to substitute that. So JD is epsilon naught del by voltage. D is the distance between the plates. Yeah. Okay, so the displacement current is epsilon naught by D del V by del T. Okay. Now, if you look up the definition for the capacitance of a parallel plate capacitor, the capacitance is given by C is epsilon naught area divided by D. So what we'll do is we'll multiply this by area and area of the plate. So JD times the area of the plate is epsilon naught area D del V by del T. Okay. But current density times the area, current density times the area of the plate is the current. So displacement current is C times del V by del T. Okay, and that's what they're asking you. Express the displacement current. There's the displacement current in a capacitor in terms of the capacitance and the rate of change of voltage. Okay, so the capacitance times the rate of change of voltage across the capacitance acts like a current. Okay, and so this current is producing a magnetic field like that. This displacement current also acts like the same current, essentially. Yeah. So essentially, if you have an infinitely long wire, so what we are saying is this: if you have an infinitely long wire and you have a capacitor in between, or an infinitely long wire like that, they'll produce the same magnetic field. Okay. Yeah. As long as the current is steady, except that if you put a capacitor in between, it's hard to maintain a steady current. You'd have to have a changing voltage and all that stuff. Yeah. All right. So here's a similar problem. Okay. So the potential difference VT between the parallel plates shown above is instantaneously increasing at a rate of 10 to the 7 volts, 10 million volts per second. So at a given time, the rate of change of voltage is that. Okay. What is the displacement current between the plates if the separation of the plates is 1 centimeter and the it has an area of 0.2 meters square. Okay, we just saw that the effective current because of increase in electric field, the displacement current, you just saw is C del V by del T. Okay, and for a parallel plate filled with air, that's the capacitance del V by del T. So the displacement current is given by that. Yeah. Epsilon naught is 8.85 into 10 to the minus 12. What are the units? Coulomb square, Newton meter square. Area is 0.2 meters square. Distance is 1 centimeter, which is 10 to the minus 2 meters. And del V by del T is 10 to the 7 volts per second. So the displacement current will work out to, okay, so here, let's take care of powers of 10. This is, that makes it 10 minus 10, 10 minus 11, 10 minus 4. So we'll say 8.85 into 2 into 10 minus 4 amperes. Yeah. And so (1.77 into 10 minus 3 amperes). So a milliampere current. Okay. So this problem says, if the electric and magnetic field strength varies sinusoidally in time at frequency 1 gigahertz, so this is a billion hertz, being 0 at t equal to 0, then, and the electric field is given by that, E naught sine 2 pi ft and B naught. When are the field strengths next equal to 0? Okay, so you guys have drawn, sine functions. Okay, this is the electric field. It's given by this is T. Okay. Okay, so the frequency, this is a gigahertz. That is 1 period. This is 1 period. And the period is inversely proportional to the frequency. Okay. And this, of course, is half a period, and so on. This is half a period. Okay, so so it's 0. The field strength is 0 at t equal to 0. When are the field strengths next equal to 0? So there'll be 0 half a period later. Okay. So period is 1 over frequency, which is 1 over 10 to the 9, 1 over second. Hertz is 1 over seconds. Okay. So that's 10 to the minus 9 seconds. So the period is that E will be 0 at t equal to t by 2 at half a period, which is 0.5 into, so 0.5 nanoseconds later. Okay. So it's 0, and every half a nanosecond it'll be 0. It'll be 0 at half a nanosecond, 1 nanosecond, 1.5 nanoseconds, and so on. Okay. when do they reach their most negative value? So it reaches most negative value. This is t. This is 3/4 of a t. Okay? So 0.75 into 10. How much time is needed for them to complete one cycle? I mean, 10 minus 9 seconds. So, I mean, we calculated that first and then answered everything else. So actually, what you would do is, so yeah. So anyway, did you guys understand that? Okay. So the most negative value, for instance, you would put that to be 3 pi by 2. This guy, and you would get that. Okay. So for instance, if you wanted for B, I'll do that again. So E is E naught sine 2 pi ft. Okay, so you want the negative value, then this one's, you want this to be 3 pi by 2. So 3 pi by 2 equal to 2 pi ft, and t equal to 3/4 1 over f, 3/4 t. That's what we wrote. Okay. But it's easier to see it in the diagram. Okay. All right, so this next problem says a radio station broadcasts at a frequency of 760 kilohertz. Okay, so this is an AM radio. At a receiver some distance from the antenna. At a receiver some distance from the antenna, the maximum magnetic field of the electromagnetic wave is detected to be that. So you guys remember what is the Earth's magnetic field? The strength of the Earth's magnetic field? About 5 times 10 to the minus 5 Tesla. So this is 1,000,000 times weaker. Okay. So the electromagnetic wave in this room, the signal has a magnetic field strength 1,000,000 times weaker. Okay. But that's an oscillating field, and so the Earth's magnetic field is steady. Okay. What is the maximum electric field strength? Okay, so you saw that E max in an electromagnetic wave, the ratio of the electric field to magnetic field is equal to c, the speed of light. Okay, so c is 3 into 10 to the 8 meters per second, and B max is 2.15 into 10 minus 11 Tesla. So 6.45 into 10 minus 3, and electric fields are volts per meter. So millivolt per meter. Okay. And then they ask you what is the wavelength of the wave. Well, the speed of this electromagnetic wave is c, and its frequency times the wavelength. So wavelength is speed of light divided by frequency. And frequency is 760 kilohertz. Okay. So the wavelength of this electromagnetic wave is 400 meters, which is roughly from here to Mainland High School. Yeah. Okay, so at what distance does a 100-watt light bulb produce the same intensity of light as a 75-watt light bulb produces 10 meters away? Okay. So there's a certain level of brightness from here to the wall, and a 100-watt bulb will produce the same level of brightness further away. Okay. So the brightness is the intensity at that level, at that distance. Okay. So the intensity is given by power divided by area. Okay, so we are assuming a light source that's emitting uniformly in all directions, power, and the area is the surface area of a sphere, which is 4 pi r squared. Okay. So what we want is the 100-watt bulbs to produce the same intensity as the 75-watt bulb. Okay. So this is power 100 divided by 4 pi r 100 square, power 75, 4 pi. The 4 pi's cancel. Okay, so r 100 square equal to P 100 or
Is the area 4 pi r squared because it's a sphere?
mm-hmm. Yeah. All right, so this is a 100-watt bulb, and that's 75 watts, and this is 10 meters. Okay, so the 100-watt bulb will produce the same brightness as a 75-watt bulb 15% further. Okay. A small helium neon laser has a power output of 2.5 milliwatts. What is the electromagnetic energy in a 1 meter length of the beam? Okay, so power output. So here's the laser beam, and in 1 second, what happens is 2.5 joules pass, millijoules pass you by. Okay, so what this is saying is if you're standing there, in 1 second, 2.5 millijoules will pass you. And in 1 second, what length of the beam passes? The speed of light is c, so it'll pass, c meters will pass you. Did you guys understand that? So in 1 second, a beam of length c meters will pass you, and the energy that will pass you is that much. Okay. So how much energy is contained in 1 meter of the beam? So energy per unit length is the energy that passes you divided by C meters. Yep. So 2.5 millijoules and C is 3 into 10 to the power 8 meters. So the amount of energy contained within so every meter length of that laser beam contains that many. Okay, 8.3 into 10 to the minus 12.
How did you go from, how did you get millijoules?
Watts is joules per second.
Oh,
Milli.
that's,
Mhm.
okay, I see it now, thank you.
Mm-hmm. So this problem says at the top of Earth's atmosphere, the time average pointing vector is just the average pointing vector is just the intensity of light. Okay. Associated with sunlight has a magnitude of about 1.4 kilowatts per meter squared. Okay, so what this means is the following. So here is the Earth, here is the atmosphere, and the intensity at the top of the atmosphere is 1400 watts per meter squared. What does that mean? So here's a meter square, and on this much area, 1400 watt bulbs are shining. That's how much sunlight is falling. And as young people, you ought to know that. So you can calculate the total energy falling on the Earth. On the top, about half of it reaches the ground level, half of it. And you have to harness only 1 part in 10,000 of that sunlight falling, and you can run the entire planet. Did you guys understand that? 1 part in 10,000. What does that mean? So let's say if it's raining $100 bills, so for every $100 bills that rain, you have to pick up only $1. Or for every 10 $100 bills, no, every $100, every $100 bill that falls, you have to pick up only 1 penny. Okay, you can run the entire planet on just solar energy. And right now, solar energy is the cheapest, one of the cheapest, solar and wind. So why aren't we running the planet entirely on solar energy?
We have an existing infrastructure.
What's that?
We have existing infrastructure built around fossil fuels.
Why aren't we running on solar energy?
Technology's not advanced enough.
So at night times, what do? You need batteries, cheap batteries. That's the problem.
Batteries are too expensive.
Right.
Not,
Yeah.
doesn't have enough capacity.
But so Yeah, they're just too expensive right now. Okay, so essentially that's the problem. All right. So what are the maximum values of the electric and magnetic fields for a wave of this intensity? Okay, so the intensity is average, and okay, let's look up the formula. So pointing vector. Okay, so the intensity is average that, and there is the in terms of average magnetic field and electric field. Okay, so intensity is that E max, oops, B max, or 2 mu naught. Okay, so part A asks you what is the maximum value of the electric and magnetic field strength. Okay, so we will E max, and what is B max? B max is E max over C. Okay. So E max okay. All right, so let's put in these values. So E max is square root of 2. Intensity is 1400 watts per meter square. Mu naught is 4 pi times 10 to the minus 7 Tesla meter amp. And C is 3 into. So what is this that we are finding? We are finding the amplitude of the electric field in sunlight at the top of the atmosphere. Okay? So that's what we're finding. All right. Let's take care of powers of 10. That's 10 and 10 to the 3, 10 to the 4, so that you'll get 10 to the 2 square root of that is volt per meter are the units. And then you have 2 times 1.4 times 4 pi times 3. So the amplitude of the electric field at the top of the atmosphere is 1,000 volt per meter. And of course, the magnetic field is related to the electric field strength by that relationship. And the amplitude of the magnetic field is 10 to the minus 6 Tesla. You got 3 times 10 to the minus 6 Tesla. And then what is the total power radiated by the sun? Okay, so here is the sun. Oops. Now we know the intensity at the Earth. We know the intensity there. This is the sun-Earth distance. Okay. So the power radiated by the intensity equal to power radiated by the sun divided by 4 pi r. Okay. So that's the sphere. So the power radiated by the sun is intensity at the Earth times 4 pi r sun-Earth distance squared. This is 1400 watts per meter squared. 4 pi. Okay, so Earth-Sun distance, we have to look it up. Okay. 1.49 into 10 to the 9 meters. Oh, no, million, 11 meters. Okay. Okay, squared. So this works out to, okay, let's take care of power. So 10, that's 22, and 3, 25. 1.4, and this is power, so it'll work out in watts times 4 pi times 1.49 squared. Okay, so 3.9 into 10 to the 26 watts. There's the power of the sun. Okay, the reason I wrote it like this is that's a 100-watt bulb. So the sun glows like a 4 trillion 100-watt bulbs. Okay. All right, so we'll do this. This next problem says a 2.5 meter diameter university communication satellite. So 2.5 meters is roughly the width of this table. So a dish this big, okay, receives TV signals that have a maximum electric field strength of 7.5 microvolts per meter. What is the intensity of this wave? Okay, so what you have is a satellite emitting so a beam, and the intensity at this dish is such that the maximum electric field strength is that. Now the intensity in terms of B max, E max, B max by 2 mu naught. You saw that. The intensity is E max, B max is E max over C, 2 mu naught. So and we already saw this last few problems ago. 2 mu naught C. All right, so what this is they give you the maximum field strength, so you can calculate the intensity at the satellite dish. So we'll calculate the intensity there. Okay. So, oops. What is the intensity of the wave? The intensity is E max is 7.5 into 10 minus 6 volt per meter square. 2 mu naught is 4 pi into 10 minus 7 Tesla meter amp. And C is 3 into 10 to the 8 meters per second. Okay, let's take your powers of 10, that's 10 minus 12. And then 7 get killed there, so 10 minus 5. And then another 8 comes up there, so that's 10 minus 13. It's 10 minus 13, and that's watts per meter square. 7.5 square divided by 8 pi into 3. What was this? This was 13. So 7.5 square divided by 8 divided by pi divided by 3. So this works out to 7.46 into 10 minus 14 watts per meter square. So that is the intensity of the signal at the dish. Okay? Intensity is power per unit area. Okay. What is the power received by the antenna? The power received by the antenna is the intensity times the area of the antenna. Okay. And it's a 2.5 meter diameter dish. Okay, so the dish diameter is 2.5 meters. So this was part A. B was the power at the dish is intensity times area of the dish. And so again, you guys realize it's not this area, it's this area that matters. Yeah? And the radius is 1.25 meters. So this will give you a sense for the communication. Okay, so the power falling on the dish is 0.37 picowatts. Okay, a trillionth of a watt, less than half a trillionth of a watt. All right, so that is the power falling there. And now let's calculate what is the power of the satellite. Okay, what is the satellite doing? What is the power received by the antenna? If the orbiting satellite broadcasts uniformly over an area, this is the area it's broadcasting over an area of 1.5 times 10 to the 13 meters, a large fraction of North America. How much power does the satellite radiate? Okay, so the satellite has to radiate such that anywhere in the US, you should be able to catch that signal. Okay? So power of the satellite equal to intensity at ground level multiplied by the area. And the intensity at ground level was 7.46 into 10 minus 14 watts per meter square. And the area, the coverage of the area was 1.5 into 10 to the 13 meters squared. So the power radiated by the satellite one watt. So this is what's involved in the satellite communication. See, you can't have this guy radiate too much because where is this guy getting his energy from? The sun. He's using solar panels. Okay, so he doesn't have too much energy at his disposal. And so the signal is weak. So satellite communication was possible when your electronics become sensitive enough where they can, with very little power, or with, so the power that the dish is receiving is a picowatt. Okay, because you could get information out of, you were sensitive enough to detect that such small signal, satellite communication was possible. If you needed a stronger signal, this would have to radiate much more power. Okay, and so, okay.
So instead of radiating more power, you more so adjust your dish to be more sensitive?
Right.
Okay.
So the more sensitive you are, the less taxing it has to be on that guy. So this kind of stuff goes on. So for instance, so you guys know how efficient solar panels are now? About 20% efficient. What does that mean?
It means that 20% is absorbed as energy, which can be transported to electrical.
Yes.
And the other 80 can be wasted as heat.
So yeah, of the 100 joules of sunlight falling, 20 joules is converted to electricity. Okay. All right, so that's 20% efficient. Now, they're trying to improve the efficiency of these guys. So let's say if somebody went from 20% to 22% at the same price. Well, right now it's a little more expensive. It's expensive. You can buy these guys, but they're much more expensive. Well, what's the big deal in that? The big deal is the following. If you get 10% more efficiency, if you had to use this much area to run the planet, now with 10% efficiency, you just have to use 10% less area. Okay? And if the lifetimes are the same, the maintenance costs are less, everything decreases. So that's why you fight for this kind of stuff. Okay? You guys understand? Installation costs, everything goes down and all that. Oops. A microscopic spherical dust particle of radius 2 micrometer and mass 10 microgram is moving in outer space at a constant speed of 30 centimeters per second. A wave of light strikes it from the opposite direction of its motion and gets absorbed. Assuming the particle decelerates uniformly to 0 speed in 1 second, what is the average electric field amplitude in the light? Okay, so here's a dust particle, and it is stopped by a beam of light. Okay. So it was going at 0.3 meters per second. And it stopped in 1 second. So let's first calculate the acceleration. So final velocity is initial velocity plus. Okay, what did the beam of light do? It stopped at the final velocity is 0. Initial velocity was 0.3 meters per second. So the acceleration the negative sign just telling you that the acceleration is in the opposite direction of the velocity. Okay, so what is the force that must be exerted on the particle? Mass times acceleration. Okay. The mass of the particle is 10 to the minus 10 micrograms, and each gram is 10 minus 3 kgs. Okay, so 3 into 10 to the minus 9 newtons is the force you need to apply to stop that guy in 1 second. All right, and how are you going to apply that force? You're going to use a light beam to apply that force. Okay. So force is pressure times area that the light beam applies. And the pressure a beam applies here, so let's look up that expression. Pressure a beam applies when it gets absorbed. Pressure exerted by radiation falling on a absorbing surface is intensity divided by C. Okay? Well, intensity you saw in terms of maximum amplitude of the electric field is 2 mu naught C. So that's the intensity and divided by A by C. Okay. So this is the intensity. There was another C there, and there is the A. Okay. So now we can calculate this. So E max square 2 mu naught C square times A is equal to 3 times 10 to the equal to the force. Okay, so the amplitude of the electric field in the beam stopping the particle is given by that. So let's put in that information. 2 mu naught Mu naught is 4 pi into 10 to the minus 7 Tesla meter amp. C is 3 times 10 to the 8. And force was 3 times 10 to the minus 9 newtons. Divided by r square. The radius, so of radius 2 micrometers. Okay. All right, so let's calculate this. So let's take care of powers of 10. This is 10 minus 12. That's 10 minus 16. So you get 10 minus 4. And this is 16 minus 4 is 12. And square root of that is 6. So you get 10 to the 6 volt per meter. Okay. And then the rest of the stuff. 2 into 4 pi into 9 into 3 into 4 pi. Okay, let me do that again. That's 12. 12, so plus 3 minus 4, 16. Yeah, 12, 6. Okay. So that's right. The 4 pi cancels. So square root of 54. So the intensity of light is 7.35 into 10 to the 6 volt per meter. The amplitude of the light beam. Okay, so if you want the light beam to stop, this guy 10 microgram in 1 second, the intensity is a million. The intensity is 7 times a million volt per meter. You guys remember what is the intensity of sunlight? The electric field in the sunlight? It's 1,000 volt per meter. So 1,000 times stronger than the, well, the intensity would be 1,000 square, 1,000,000 times stronger than the sunlight. Okay. By the way, do you guys remember solar sails? I think we just launched a solar sail today.
Oh,
Check it out.
how durable are they to like asteroids or?
Oh, well, asteroids. I mean, little dust particles will tear them up.
Oh, okay.
So the James Webb Telescope has thin materials on the other side, 6 layers of that to block radiation and stuff like that. No. So, but yeah, it was funny. So check it out. Okay, so one last problem. What is the frequency of a 193 nanometer UV radiation used in laser eye surgery? Yeah. Okay, you'll sort of see why we use this. Okay. So C is frequency times, okay, and lambda is C over F. Oh no, we're finding the frequency. Okay, so again, You guys remember uh, the smallest size? So here's your probe. That's the wavelength. The smallest size it can see is roughly equal to the wavelength. Okay. The wavelength of this UV laser is 193 nanometers. Okay. So the smallest thing it can burn, this laser can burn, is that. Okay. A tenth of a nanometer is one cell. So this is 2,000 atoms worth. And a cell is smaller than that. So this laser can burn cell by cell. So you guys know how the laser surgery is done? Okay. So what they do is, so here's your eyeball, and so here's your cornea, and here's your lens. The cornea does 75% of the bending of the light. This guy does only 25% of the bending of the light. And here's the image formed on the retina. Okay. So if your eyeball is not focusing on the retina, what they do is they change the shape of the cornea and make the image form there. Okay. Now, what they do is they'll cut open the cornea, cut a slice on the cornea, peel it back, and so and then burn cells using a laser. And then put it back, and the cornea heals. Okay? So they use this wavelength so they can vaporize cell by cell. If they used a long wavelength, then that laser would not be able to burn small areas. Yeah, so you guys understand now? So that's where the wavelength comes in, okay? Do you know anybody who's had laser surgery? Yeah. All right. So the frequency is that. So this is 300 times 10 to the 15 divided by 193 hertz. Okay, so that's the frequency of the laser beam. Assuming the accuracy with which the electromagnetic radiation can ablate the cornea is directly proportional to the wavelength. So the area actually is roughly equal to the area. How much more accurate can this UV radiation be made than the shortest visible wavelength of light? The shortest visible wavelength of light is lambda short is 400 nanometers. Okay, and so laser divided by 400 nanometer divided by 193. Okay, so essentially by a factor of 2. Okay. Anyway, so you guys see, the shorter the wavelength you use, the smaller the chip, smaller the tissue you can chip away, essentially. Okay. All right, guys. So.